Welcome to your 6.2 lesson. Today we're going to summarize a linear relationship with the least squares regression line. So imagine, if you will, a scatter plot, and then we've got a line going through it. Why do we call it the least squares regression line? Because we want to make the sum of the squares of the vertical distances from the points to the line as small as possible. You may be going, I cannot even think of what you're trying to say. Well, let's look. Let's consider a situation where we're looking at the number of caribou and hundreds of caribou and the number of wolves in some grassland area. So let's look here. So it seems to be that as the number of caribou increase, the number of wolves increase. That makes sense since caribou are a delicious treat for the wolves, and so where there are caribou, there will be wolves. So that makes sense. And if you look, we have modeled the situation, which does seem to be roughly linear, with a line. Now, the line does a fairly good job of predicting how many wolves to expect based on the number of hundreds of caribou that you have, but it's not perfect. It doesn't hit every point. It could not hit every point and remain linear because there is scatter among the points. So, for instance, here at x equals 20, what was observed was actually about 60 wolves, but what would be predicted by the line would be somewhere around 53, maybe 54 wolves. So there is this distance from one of the points of the scatter plot and the linear model. And so what they try to do is minimize the amount of error. Now, because some of these are above and some are below, the positive and negative nature cancel each other out. So to really be able to measure how much error there is, you have to get everything in terms of positive. So what they do is they square these distances. So you square this distance, square this distance, square this distance, this distance, this distance, this distance, this distance, and you come up with a value. And what you try to do is you try to find the line that minimizes the square of the sum of the squares of those distances. And that is our least squares regression line. And it is y hat equals a plus bx. Now remember, we put a hat on our y because we are having a statistics party, and just like at a birthday party, you got to have hats, and you want to differentiate between the predicted y value, which remember here for x equals 20, the predicted y value is about 53, 54, and the observed y value is 60. So we need to differentiate between those two. So y hat is the predicted y value, and a plain y is the actual observed y value. So y hat equals a plus bx. Now in statistics, typically a is a y-intercept and then b is the slope, and we do write the y-intercept first. So whether you are using a fancy CAS calculator, which if you are, you're going to make your life a lot easier, or if you're using some other calculator that's just going to help you crunch numbers, you need to have your list of data points. Okay, you need to have all your x's and y's. You need to know what they are, and we call our sample size n. Then, using the data pairs, if you are going to actually go through and calculate the equation of the least squares regression line, you're going to need to make some columns, because you're going to need the sum of the x's, the sum of the y's, the sum of the x squares, the sum of the y squares, and the sum of xy. And then you're going to need the sample means, x bar and y bar. So for finding the slope, you're going to use the following formula. You're going to use that b is equal to n times the sum of the product of xy minus the product of the sums of x and y, all divided by the difference between n times the sum of x squared minus the sum of x, the sum of all the x's squared. So for finding the y-intercept, you're going to take the slope that you just found with that big old formula, which you don't need to memorize, you just need to be able to use, and you're going to take x bar and y bar. And you're going to calculate a with a equals y bar minus b times x bar. It's an interesting fact that x bar and y bar always lie on the least squares regression line. And remember, y bar is the mean of the y values, so you just take the sum of the y's and divide by n. And x bar is the mean of the x values, so you just take the mean of you take the sum of the x's and divide by n. And b is the slope that you just calculated. Okay, so if we use the data that we used in the last lesson, where we've got miles traveled and then the minutes it took to travel those miles. So it takes 6 minutes to travel 2 miles, 5 miles took 9 minutes to travel, 12 miles took 23 minutes to travel, and so on. So the sum of the x's, we just add them all up, we get 58. The sum of the y's, you just add all those up, you get 118. The sum of x squared, you actually square your x terms and you add those up to get 596. Now for our calculation for slope, we don't need the y squared, so we didn't repeat that here. We left those off. But the x times y, that product, you're going to calculate that. So 2 times 6 is 12, 5 times 9 is 45. So you calculate your products of x times y, and then you add those up, and then you plug them into the appropriate place in the formula for b. Okay, so you can see n was substituted where n is supposed to be substituted here and here, and the sum of the products of x and y are here. The sum of x is up here and down here. Down here it's squared. The sum of the y's, and then the sum of the squares of x. And when you calculate all that, it rounds to be 1.70. So then, finding the y-intercept, we need to step back and find x bar and y bar. So for y bar, we take the sum of the y's, so 118, and divide by n, so 7, and we get 16.857143. And then for x bar, we do the sum of the x's divided by 7, so 58 divided by 7, and we get 8.28, blah, blah, blah. And then for the y-intercept, we plug those values into our formula. So we have A equals y bar minus B times x bar. So we plug in what we know. Notice that we don't round until the end because we don't want to have rounding error. We don't want to compound it. So we take our exact value for y bar minus our exact value for the slope times our exact value for x bar, and we get 2.76737273, and we round it to 2.77. So our equation for our least squares line is y hat equals 2.77 plus 1.70 times x. Okay, so you can do that and you can use those formulas, or you can find these values by entering the data into 2 lists in a spreadsheet in your CAS and running a linear regression on the data. Much easier to do. Many fewer mistakes to be made doing it. So I suggest that you find your 1.3 notes from the finite math semester of this class, or re-watch the 1.3 video that I'm going to include as a link in the same email that you had the link to this video. If I forget, remind me, and review how to put this into your calculator and do the linear regression that way. Okay. So if we're going to graph this by hand, you need 2 points. So one thing you can always use is the x bar, y bar, so 8.3 and 16.9. You can plot that. And then just pick a reasonable value for x and plug that in. So try, say, x equals 5. So then y hat is going to equal 2.8 plus 1.7 times 5. Okay, just plugging in 5 for x, and you get 11.3. So you get another ordered pair of 5, 11.3, and that makes it easy. Again, x bar, y bar will always be on your line, so that's always a good place to start. You could also use the y-intercept. You could always plot 0, 2.8. That makes it really easy to do also. All right. So again, graphing, you're going to use 2 values in the range of x, compute to corresponding y values. You can use your y-intercept and the x bar, y bar. Those are always nice. Plot the points and then just join them with a straight line. Okay, so here is with the miles and minutes example. Here are the 2 points that we chose to use. And so you can see it's really easy then to draw in the line. Okay, one thing we want to be able to do is use the equation of a least squares line to make predictions. So the predictions are going to be made for a particular x value, so you want to choose an x value within the range of the x values that you are given, substitute the selected x in the least squares equation, and then determine the corresponding value of y hat. So again, our equation was y hat equals 2.8 plus 1.7x. So to predict the time to make a trip of 14 miles, you would plug in 14 for x. And so you have 2.8 plus 1.7 times 14, and that gives you y hat equals 26.6. So according to the least squares regression equation, a trip of 14 miles would take 26.6 minutes. Sometimes you're going to hear some of this vocabulary. Interpolation is using the least squares line to predict y hat values for x values that fall between the points in the scatter diagram. Extrapolation is predictions beyond the range of the observations. It's not a good idea because you don't know if the conditions that have been true will continue to be true. The current trend may not continue. So you don't want to go far outside of the original range of x values. The least squares line can be greatly affected by extreme or influential data points, so you need to be aware of them. And a statistic that's related to R that we're extremely interested in now that we know that the linear relationship, we have this model for the linear relationship between x and y, is the coefficient of determination, which is R squared. It is a measure of the proportion of the variation in y that is explained by the regression line using x as the predicting variable. So if R is equal to 0.9753643, then what percent of the variation in minutes is explained by its linear relationship with miles traveled? What percent is unexplained? Well, the percent that is explained is R squared, so we're just going to square the R, and we get 0.9513355. So about 95% of the variation in minutes, our y value, is explained by the linear relationship with x, the miles traveled. So if 95% is explained, there's only 100% of anything. So 100% of the variation minus the 95% that is explained leaves 5% that is unexplained. Okay, that's it for Unit 6, Lesson 2. Go ahead and do your problems to try on your own. Thank you for taking good notes, and I will see you in class. Have a great day.